Hello, I am Alan Burnham, formerly an adjunct professor and still affiliated with Stanford University. I prepared this presentation for the Basin and Petroleum Systems Modeling Group at Stanford. Vitrinite reflectance is commonly used to calibrate paleothermal history models, but most people using it don't have a very good understanding of the physical chemistry and physics behind vitrinite reflectance. That is the emphasis of the first part of this talk, which forms the basis for the Vitromat family of reflectance models and the derivative family of EZ%R0 models. I then discuss how those models have evolved recently and why you should consider using one of the more recent versions instead of the original values. Vitrinite reflectance has a century-old history starting with coke. In the lower right-hand corner, you can see a review that I found published in 1922. It reviews a paper published in 1921. The interesting thing about this review, which talks about using reflected light to characterize coke, is the statement that this method of examining coke is interesting, but it does not impress one as likely to yield information of practical value. Of course, the entire concept of vitrinite reflectance is based on this concept. So it seems like that person was not predicting the future very well. And in fact, in general, when it comes to basic research, we really don't know how other people will use basic research in the future. It generally has very unpredicted applications. A next step up to 1952 to a paper by McCartney. He reviews some of the early work that tried to relate vitrinite reflectance to the maturation of coal. The first measurements were done by Hoffman and Jenkner in 1932. The concept was elaborated and put on more solid ground during the mid-30s to mid-40s by the papers up in the upper right-hand corner. And then in the 1950s, we really started getting into the fundamental optical properties that are underlying vitrinite reflectance. We'll start in the middle of the page here with the Lorentz equation. And all the three equations which appear on this page will come from the 1800s. The Lorentz equation relates the refractive index to the number density, rho, and polarizability, alpha, of the molecules in the material. And here you see some results plotted by McCartney and Ergen from various workers, including their own work. In addition, there's the Lambert-Beer law, which is an exponential decay in the intensity of light as a function of distance into the sample, L. McCartney and Ergen used the convention of NK as being the effective absorption constant. Other people just use K. So you always have to be careful when you're looking at these equations that you have properly identified the right convention of that particular worker. But in this particular case, you see that the index of absorption increases exponentially as the hydrogen to carbon ratio decreases towards 0. In graphite, it's an order of magnitude higher than a starting coal. The absorption in an immature coal may be due to some large aromatics and also some nitrogen-based compounds, but you can see that the absorption term gets much larger as you go to smaller hydrogen content. The final equation we have here is the Fresnel-Lambert equation, which was derived sometime in the mid-1800s. The refractive index is actually a complex number, with the first term being the refractive contribution and the second term being the absorptive contribution, which is multiplied by I, the square root of -1. Multiplying this complex refractive index by its conjugate gives the two squared terms in the numerator and the denominator, where K again is the absorptive contribution. The subscript O indicates the refractive index of immersion oil, which has no absorptive term. Looking at the figure, you can see that the reflectivity increases exponentially as the H/C ratio tends towards 0, with an asymptotic limit of graphite, of course. At the higher H/C ratios, the increase is due largely to densification, but is due primarily to absorptivity at the lower H/C ratios. So let's talk a little bit more about how the refractive index originates in the first place. The refractive index is due to light going through the material, and the oscillations of the electric field cause the electrons in the material to oscillate along with that electric field. Now, there's two kinds of electrons in the media we'll be talking about. One are the localized electrons, and the other are delocalized electrons. For localized electrons, the appropriate model is the Drude-Lorentz model. This was again developed back in the 1800s. And you can think of it as an off-resonance interaction with a transition. And here, this is an example from Wolfram where you can play with the oscillator frequency and the damping parameter gamma, and the dielectric constant, which is a square of the refractive index, increases as you get close to the maximum absorption. Then it decreases, it becomes negative before heading back towards 1. And the damping parameter causes the width of the absorption coefficient to increase. For delocalized electrons, the appropriate model is a particle in a box, which is a standard fare in an undergraduate physical chemistry class. And what this really says is that you have a standing wave where the wavelength is an integral number of the length of the box. And the more waves you have in the box, then the higher the energy level. And so there's a well-known spacing of these energy levels according to, that depends on the quantum number of the wave and the length of the box. So this is appropriate when you get to polyaromatic materials where the electrons can move over large distances, meaning 10 to 100 atoms in length. And so that gives you the absorption bands that give a carbonaceous material basically its black color. So the localized electron contributions to the refractive index can be estimated by group additivity rules. And there was a book by Van Crevelen in 2009 that talks about this in detail. But basically, if you go back to the Lorentz equation, remember that the refractive index is related to the polarizability and the number density. And you can break down the polarizability of any given molecule into the polarizability of its individual atoms. And the polarizability of those atoms will depend on its hybridization and its bonding configuration. So Van Crevelen shows all these group terms that you add together to get the polarizability or the molar refraction. And you can see that the carbon numbers to a first approximation are about 2.8, hydrogen about 1, nitrogen about 2.8, sulfur around 8, oxygen about 1.2. And so the first concept I want to introduce is that when you eliminate hydrogen and oxygen, you're going to get a higher molar refraction. And that's what maturation does. It eliminates hydrogen and oxygen. So in the polymers down there at the bottom, you can see that polyvinyl acetate has oxygen, and it has a slightly lower refractive index than polyethylene. Polystyrene, PS, it has a higher refractive index, and you can understand that really by looking at the cyclohexyl and phenyl groups here. The hydrogen content, hydrogen doesn't have a very high polarizability, but it has enough volume that it lowers the density of carbon atoms. So even though the carbon has a higher molar refraction in this hybridization, there's fewer of them per unit volume. So in benzene, basically what happens is the hydrogen gets eliminated, and so you can pack more carbons into a given volume. And so you'll end up with a higher refractive index. That's what is encapsulated in these equations up here. So now let's consider the various contributions to hydrocarbons, diamond, and graphite. It's often discussed that vitrinite becomes more reflective because it becomes more aromatic. And that's partially true, but it's not the entire story. So let's take diamond, for example. It has a refractive index of 2.42, which is greater than a mature kerogen, 1.8. But as you know, diamond is a perfectly clear material. And the reason it has a high refractive index is because it has a high density, 3.52 grams per cubic centimeter, compared to graphite of 2.26 grams per cubic centimeter. And because of that high density, it has a high reflectivity, around 6%, which is really very high for any kerogen. Comparing that now to anthracite, the refractive index is starting to become anisotropic. In the maximum polarization, it's a little over 2, and the minimum, it's a little less than 2. The density is quite a bit lower than either graphite or diamond. So you can see right now that density of carbon atoms is one of the contributions to the lower refractive index. It has a reflectivity around 4% for a hydrogen to carbon ratio of around 0.3. Now graphite becomes more anisotropic. Now the maximum refractive index along the aromatic planes is 2.15, and the perpendicular is 1.81. Now remember 1.81, which is why I've got it highlighted in blue. It turns out the reflectance is much more anisotropic than that, 15.6% in one direction, 2% in the other direction. And the reason for that is because this particle in the box electron contribution is only along the planes of the aromatics. And so that gives you a high absorption coefficient, 0.66, compared to a perpendicular to the rings. There's essentially no absorption in the visible range. So that is somewhat surprising, but these are the measurements that have been made. So now if we go on the left-hand side, you can see the refractive index as a function of the hydrogen to carbon ratio for various hydrocarbons. I plotted here solids and liquids. When you have a hydrogen to carbon ratio around 2, you can get both polyethylene type materials, which are solids, and things like hexane and decane that are liquids. And so immediately you can tell the effective density. The refractive index changes by about 0.07. As you go to a lower hydrogen to carbon ratio, those two, the solid and liquid, tend to converge. And if you extrapolate that trend all the way to 0 hydrogen to carbon ratio, you get a refractive index of about 1.8, which is very interestingly the same as you have for graphite. So that all works. So in the small inset graph, so you ask yourself, well, what is really the defining variable? Is it hydrogen to carbon ratio, or is it really density? And so here you see the correlation between density and refractive index is pretty good. And so as I said before, what's really happening here is hydrogens are not very polarizable, but they take up volume. And so as soon as you get rid of the hydrogens, you can pack more carbon into the volume, and the refractive index goes up. In addition, and this is where the anisotropy of graphite comes in, when you start getting the large polyaromatic rings, you also get this absorptive term, and that takes your reflectance up from around 2% to up around 15% in that direction. So anyway, to summarize, the primary contribution to reflectance for graphite is the absorptive term parallel to the aromatic ring. So now we can go back to the concept of a few slides ago of comparing in for diamond with the minimum for graphite. And that tells you a little bit more about what you get in terms of increase of refractive index due to densification. So here are the equations which are shown there, and we can plug in the refractive index, and we can solve for the for this term here, the R0 rho over M 0.6, and now this ratio here gives you the ratio of diamond to graphite. You plug in this information into this particular equation, and what you find is that the refractive index, just from this simple density calculation, uh, should be about 1.724, which would give a reflectance of about 0.4%, similar to an immature kerogen. Now, if we actually use the measured value of 1.81, we get a reflectance closer to 0.8. So you can see here that the densification contribution to what might be happening in kerogen is comparable to what is changing over the oil window. Oftentimes you see pictures about the reflectance increasing because of the polyaromatic material forming, but in fact, during the oil generation, what you're really doing is you're more concentrating existing aromatic material, which may be mostly small rings, and that's a very important part of the contribution to the increase in reflectance, not strictly the idea of getting large polyaromatic rings. So we can see now, if you just take the carbon density term, you get this curve here, and that's really much lower than you would expect. So here now, if you add in an absorption term of 0.1, you get something which is a lot more reasonable in terms of the kinds of reflectance that you see from kerogens in the relatively low immature, low and slightly mature range. Now, as you go up higher in maturity, that's when you start actually getting the aromatic rings to fuse to each other. And when they fuse to each other, they eliminate hydrogen and methane. And whether or not they eliminate hydrogen or methane depends on things like the temperature and the pressure that are informed, that are relevant either for laboratory or geological conditions. Now, this was all understood back sort of the 1980 time frame. This shows now the hydrogen and methane evolution profiles for different materials here. And during the oil generation phase, and you get a lot of oil from essentially an algal kerogen here, this is primarily concentrating organic matter. And then the methane formed here and the hydrogen formed here are really due to the aromatic rings fusing to each other and eliminating the residual hydrogen and methane. So this process out in here, above oil generation, is the thing that provides this long pi bond resonance length for a broader and stronger optical absorption. So the general concept that I introduced in the 1980s was that if you have a chemical reaction model that can calculate the composition of kerogen, you can use that composition to calculate reflectance. And so these are the elemental balance equations that you can write down for any hydrocarbon containing oxygen into these various products. And the calculation of the hydrogen to carbon ratio and the oxygen to carbon ratio are given by these equations, where the variables are defined here. Now, based on McCartney's work, you could get pretty much a straight line if you plotted vitrinite reflectance versus a hydrogen to carbon ratio. This was their dashed line. Now, it looks like there might be a little bit of curvature here. The original line was here. That may be too much. Maybe that's something that still could be looked at in more in the future. The original work drew correlations not only with hydrogen to carbon ratio, but also weight percent carbon. But the hydrogen to carbon ratio seems to be the one that works a bit better. Now, a few years ago, Søren Nielsen and co-workers brought back this idea that the break in slope of calculated reflectance versus depth was not strong enough for easy percent R0. And this is not really new. Ulrich Ritter, a few years after the easy percent R zero model was published, made essentially the same comment and had a proposed algorithm, but most people still use this algorithm. Well, this paper brought this question back up to the fore. Now, what we'll talk about now is that this lower term here is probably not correct, and it's probably due to the fact that they use too many measurements from shales, which are compromised either by measuring bitumen or by suppressed true vitrinite in the presence of an oil-prone kerogen. And we'll talk about both the evidence for both of those in the future. However, this part is probably correct. It's consistent with what other people said back in the 1990s. And so it's something we need to take a look at again. Now, the other consideration that happened in the 1990s, and remember here, in the 1980s, the kinetics of transformation were making rapid progress, but there still was a long ways to go. So the original measurements here of the activation energies and frequency factors were not as good back then as eventually they became. And it looked like the frequency factor would be about 10 to the 13th reciprocal seconds, which was certainly plausible within the range of transition state theory, but certainly not definitive. As time went on and more and better measurements were made, it looked like the most probable value of the frequency factor was between 1 and 2 times 10 to the 14th reciprocal seconds. So, so I started thinking about, well, maybe this is the frequency factor that really ought to be used in these vitrinite reflectance models. About that time, Ken Peters approached me and said, you know, they were having trouble matching data in the Alaska North Slope, and they had very well-constrained heat flow estimates as a function of time. So they were concerned about the disconnect that they were getting between calculated and measured vitrinite profiles. So I went back and used the knowledge from the previous slide to develop a new version of easy percent R0, which actually matched those profiles very well. And the two characteristics are a frequency factor of 2 times 10 to the 14th reciprocal seconds and a sharper break or dog leg in the reflectance versus temperature. But it's an improvement, but easy percent R0 did not match laboratory data very well. In this first plot, you see the original vitrimat sort of split the difference between what was thought to be vitrinite reflectance in oil-prone shales and true vitrinite reflectance from coals. Depending on how you're going to use this, you might say, well, this was either a good or a bad thing to match this data. But as we really understood more over the next 20 years, this is really not an accurate reflection of vitrinite reflectance. We'll talk about more about that later. This is what the model should agree with. And as you can see, there's a fair discrepancy between the calculated reflectance and the measured reflectance for true vitrinite in hydrospiralysis. Over the next 20 years, there were a lot more measurements made. And so now I've plotted this same sort of data here, reflectance versus temperature, for both 72 hours and 24 hours. And although there's an improvement in the agreement with true vitrinite and the model calculations at high temperature and high conversion, there's no improvement down here. So you can see that the DL model still has a problem. So I tried lots of different options to try to get the agreement to be better. And what I found was a better simultaneous agreement of geological data with lab data uses a frequency factor of 1 times 10 to the 15th reciprocal seconds. And so now here is the calculation of a new version. There's actually two versions of it. Vitrimat 2018, which uses the full element balance calculations, and the easy percent R0V, which essentially is designed to match the Vitromat model, but with fewer parameters. So you can see this agrees much better with the coal maturation trends at laboratory data than the original values. There was a preprint recently came out by Lohr and Hackley 2021. They basically added a little bit more data, but not really a whole lot of new information that reinforced the idea that the coals here in hydrospiralysis and the shales here in hydrospiralysis differ. And the reason really is that this is not truly vitrinite. This is something more likely to be bitumen reflectance that is being reported. Which leads to this next plot over here. The Vitromat formalism allows you to put into any hydrogen to carbon ratio in kinetics that you want to calculate the reflectance. And for the vitrinite, those parameters give this curve here. If you put in something for more appropriate for bitumen, you'll get this curve. And that will actually then agree much better with this data over here. The one thing I would like to point out also here is that the DL and the V versions of EZ%R0 really agree pretty well. There may or may not be a way of distinguishing which one of these is better, but they certainly have a milder break in the oil generation than basin R0, and they both have a higher reflectance than EZ%R0 in the high maturity range. So Vitromat 2018 was calibrated against more compositional data than the original Vitromat model. So one would presume that it's better. One of the issues, of course, is that there's still a disconnect between this data from Senfli and all the laboratory experiments. Now the question is, is this really the best representation of coal, or is there more scatter that really would merge these two clouds? And so I think one potential improvement for the future is to really look more about what is the real range of variability of the natural maturation curve versus the laboratory maturation curve. Is this in other words, is this a real difference, or is this a sampling difference between different kinds of coal materials? But in any event, you see that the calculations of measured carbon versus calculated carbon, measured reflectance versus calculated reflectance, reflectance versus hydrogen to carbon ratio, all these comparisons are really quite good, even though there could in principle be some refinements down the road. Now, I also made a few more comparisons since publishing that improved Vitromat model. Here's data from CalRuth in 1991 and the Penn State database. So these data sets were not used in calibration of this model. And you can see it agrees pretty well. Here's now some data from Bertrand in 1983. The one thing I would notice here is that the Vitromat model is published, started with a oxygen to carbon ratio of 0.35, and that could be increased easily to go to lower rank coals if in fact that were of interest. Now, a question which arises is whether or not you should expect the same relationship between the fraction of oil generated and vitrinite reflectance in the laboratory and in nature. There's no theoretical reason a priori that you should. It basically asks whether or not the frequency factor and activation energy of oil generating kerogen are close enough to the appropriate frequency factor and activation energy for the primary increase in reflectance. And if they're pretty much the same, you should have the same relationship. But if they're not, then you could have a shift either one way or the other. And in fact, if you use kerogen data using this frequency factor of 2 times 10 to the 14th, you find that there is a disagreement between the fraction of oil generation and EZ%R0. The DL model by design matches those. And the easy percent R0V model again has an offset because the frequency factor, which was 1 times 10 to the 15th for the oil components and 2 times 10 to the 15th for the gas components, causes those to split. And this is something that probably should be investigated further in the future. But as a practical matter, if you're interested in modeling the natural environment, these were fit so that they would give the same answer. These two will give the same answer geologically, so it makes no difference. It really is a question of addressing the laboratory data, and as we showed, the laboratory data actually works better with the V model than it does with the DL model. So the improved Vitromat algorithms can, as I mentioned earlier, can be used with any sedimentary organic matter. Here's now data of Hackley and Lewin for types 1, 2, and 3. And here's now the calculated reflectance and or the measured reflectance versus temperature, the calculations being the lines and the data being the measurements. And you can see the 3 versions of Vitromat, which are based on different starting elemental composition, agree quite well with the data. The other point here is that there has been a discussion of what is the relationship between vitrinite reflectance and bitumen reflectance. So there's lots of data here that has been plotted, and the calculation here is for the bitumen reflectance of type 1, the bitumen reflectance from type 2, and of course the third one would be the vitrinite. So you can see that the bitumen reflectance from a type 1 and type 2 are slightly different, but most materials obviously we're concerned about are from type 2 materials, and they follow along very much along the experimental data here, the red line. And I'd like to also point out that even though there's a difference in composition between these two materials to start with, by the time you get up into the 1 to 1.5 range, they pretty well merge together. And this is consistent with the difference being oil-prone components. And as soon as those oil-prone components are generated, then you're not going to see much difference. I'd now like to move back to this issue of suppression of vitrinite reflectance and what is causing it. It turns out that this has been controversial for decades, but nobody had published any experiments until Ken Peters in 2018 about showing that in fact oil-prone kerogen the oil components generated do in fact interact with the vitrinite to make it have a different reflectance value than it would be if it were just pure vitrinite. Somebody had told me that they had done experiments along this line in the early 1990s. They had never published it. So I'm not in some sense surprised by the answer, but the surprising thing is that nobody ever published it until just a couple years ago. So here's now the data. This is now the vitrinite reflectance as a function of temperature in hydrous pyrolysis of mixtures of a humic coal with Green River kerogen and some cementation material. And what you see is that when you add a lot of oil-prone kerogen, the reflectance of the true vitrinite decreases, or it does not increase as much, depending on your perspective, in the main oil phase, which is sort of here. And this is because the components of the oil are actually chemically reacting with the vitrinite to make a more hydrogenaceous material, which has a lower reflectance, as we talked about earlier. So here's now the reflectance of vitrinite or bitumen as a function of temperature. Here is the vitrinite, and here is the bitumen. In this particular case, since it's a synthetic rock, you really have no trouble distinguishing between the vitrinite and the bitumen. And you can see there's clearly a difference between those two. And that was some of the basis for the bitumen reflectance model that was derived using Vitromat. So now I'd like to summarize what I've gone through here. Vitrinite reflectance increases due to a combination of densification of carbon atoms and aromatic condensation reactions that give long absorption lengths in this particle in a box type concept that essentially gives you high absorption coefficients parallel to the aromatic rings, but not perpendicular. And the anisotropy of graphite helps put the densification and aromatic condensation reactions in proper perspective. They're both important. Densification more in the early stages, aromatic condensation in the higher maturity range. The evidence is very strong that EZ%R0 underestimates vitrinite reflectance at high maturities. And so that's one of the reasons why I would encourage you to take a look at either the DL model or the V model and make sure that you really have a good reason for using the original model. I suspect you'll find that the later models are better. And one of the things that distinguishes these two is that they have a sharper dog leg near the end of oil generation that gives you higher reflectance at higher maturity, which is more consistent with the aromatic condensation reactions giving you these strong absorption contributions. The EZ%R0V model is derived from Vitromat 2018, and it uses a higher frequency factor. So that will give you a different relationship between a reflectance in oil generation in the laboratory and in nature, because the oil generation frequency factor is on the order of 1 to 2 times 10 to the 14th, and in the Vitromat model for coal, it's in the 1 to 2 times 10 to the 15th reciprocal seconds. Vitromat 2018 also inspired EZ%R0B for bitumen reflectance. And so if you want to calibrate in a shale that doesn't, an oil-prone shale, that's the model you should be using, not EZ%R0 or EZ%R0V. And finally, vitrinite reflectance suppression is real. So vitrinite in oil-prone shales is misleading. If you really are trying to calibrate against vitrinite, either use coals or shales that do not have any oil-prone kerogen. Both are okay, but you need to avoid oil-prone components in the shales in order to get true accurate vitrinite reflectance values. Anyway, thank you for your attention, and hopefully this helps put in perspective the factors that led to the new Vitromat and new EZ%R0 models that have been published in the last couple of years. Thank you and goodbye.